So with the second derivative and its tools sort of behind us, we can start to turn our attention to curve sketching and sort of build on what we did in pre-calculus. Whether you had that here or not, or I know for some of you it's been a while, and we'll kind of go over some of the basics next lecture, because right now we're going to talk about vertical asymptotes for graphs. That's vertical and horizontal asymptotes are sort of the last thing that we need before we can uh, pretty much, sketch the graph of anything really that's sort of presented to us out of, the realm of rational functions and, polynomials. Um, and in order to do that, we'll, sort of look at a candidate function of x plus 1 over x minus 1. And as we, have seen, definitionally, a vertical asymptote, right, is when a one-handed limit, right, goes to plus or minus infinity, right? That's what it is by definition. From some point wherever you are, you go to plus infinity, you go to minus infinity. Either way, that's a vertical asymptote. And in pre-calculus and in previous lectures, if we looked at a function like this, we would say right away, oh, well, something's going on at x equals 1, right? Because there our denominator equals 0, and so we run into something bad, right? Either we run into a hole or we run into a vertical asymptote, okay? And fairly clearly, we don't run into a hole, right? Because this doesn't factor. Okay, and I'm going to spoil um, this for you, right? The limit as x goes to 1 from the right, right? So one of our one-handed limits of x plus 1 over x minus 1, it equals positive infinity, okay? And there's a couple of different ways that we can go about sort of considering this, right? And one of the first ways you would think would be to take a series of test points, right, getting closer and closer to 1, and, plugging those in, seeing that you get something real big, and, looking at its value. And that absolutely works. But I want to present to you a more intuitive way to go about it, okay? And it involves two things, okay? The first thing it involves is this fact right here. So a number, if I divide it by a really tiny number, I get a big number, right? This is how in inverse relationships works, right? Similarly, if I take a number and I divide it by a really big number, I get a really small number, right? 1 divided by 1,000 is pretty small. 1 divided by 0.00001 is very, very big. Okay. And so we're going to sort of use this concept to analyze this. Okay. Rather than thinking about, okay, well, what like numerically happens if I put in, 1.001. Let me type that into a calculator. Let's sort of think about what happens as we put a number that's just bigger than 1 here, right? We're going to get a number just bigger than 1 plus 1, or 2 plus a little bit. And then here, when we subtract 1, we're going to get something that's just bigger than 0. So what that means is we're going to have this situation, right? We're going to have a positive number, right, divided by a very tiny positive number. I guess we'll change the scale, right? Some positive number divided by a very tiny positive number, right? 2 point something divided by 0 point something, which means this is going to give us a very big positive number. And so that's how we know it's going to go to positive infinity, right? Similarly, right, if we take the limit as x goes to 1 from the left of x plus 1 divided by x minus 1, using sort of a similar idea, where's this going to go, right? Well, something just less than 1 plus 1 is going to be something just less than 2, which is a, moderately sized positive number. But then what happens here? When we take something just less than 1 and subtract 1, we're going to get something just less than 0, right? So we're going to get a very, very small negative number, which means since regular sized number divided by tiny number equals big number, this is going to give us something that's very, very large and negative, right? Where this is a negative sign, not a fraction, right? And so that's sort of how you can reason through this. Now again, earlier in the quarter, we talked about all these sorts of other ways to go about this. And all of those are absolutely valid. And you can totally, use those ideas. This is just an alternate way to think about it. And this works anytime you have some, rational function, some polynomial divided by a polynomial. Let's take a look at another function and sort of try to use this information. All right, let's say g of x is x squared over 4 minus x squared, right? This is a rational function. We have some polynomial divided by a polynomial here. And we'll notice this will factor, right, into x squared over 2 minus x times 2 plus x, okay? And, well, it looks like we're going to have a 0 at x equals 0, but that's not quite as important as looking for the vertical asymptotes, right? And the vertical asymptotes are going to happen when our denominator equals 0. Or rather, those are our candidates, right? We could have some totally different behavior. In this case, since these factors are only in the denominator, right, they're going to give us a vertical asymptote, right? If the denominator and the numerator are both equal to 0 at some value, that's a different situation. And we can deal with those as they come up, right? So, there's two zeros here, right? And we need to consider them, each on their own, right? We need x goes to negative 2 from the left, x goes to negative 2 from the right, x goes to 2 from the left, and x goes to 2 from the right, okay? And here's how I want you to think of it. So since we're approaching values that end up as 0 in the denominator, we know we're always going to get this situation, right? Some number divided by a really, really small number. And so the question now becomes, what is the sign of the thing when it gets big? That's going to tell us if it's going up to positive infinity or negative infinity, right? And here's how we can think of it, right? I might actually give these a bit more room. So let's think what's happening as x approaches negative 2 from the left, right? Notice that here, we're always squaring it, right? So that means that no matter what our input is, the numerator is positive, okay? So then what's happening here and here? Well, let's take a look here on the left first. As we approach negative 2 from the left, we're taking 2 minus that value. But this is a negative number, So it's actually 2 plus that value. And so that means it's always going to be positive. What about here, right? This is the little bit trickier one. Well, as we have something just a little bit more negative than -2, when I add 2 to it, it's going to give me something negative and very, very small, right? This is where we're getting the small number in the denominator. And so what that means is that as this in absolute value gets very, very large, the sign of these individual terms is positive, positive, negative. So that means there's an overall sign of negative, and we can see that the limit as x goes to -2 from the left of g of x is -infinity. Okay, let's take a look at this one now. As we approach -2 from the right, we can see that we're still going to have positive in the numerator, but then what's going on in the denominator? Okay. Well, here on the left, our same logic from before actually still applies, right? Because we have 2 minus some negative number. So what if it's now a little bit to the right of -2? It's still a negative number, and we're still, doing 2 minus that. So it's really 2 plus, the absolute value, which means this is positive. And then what's happening here? Well, we have 2 minus something a little bit to the right of 2, right? So, maybe 1.9. But when I do 2 minus 1.9, I end up with something positive. So that means it's going to be positive. Small, but still positive. So that means that as this guy, blows up, we're going to have positive divided by a positive times a positive, which tells us that the limit as x goes to the -2 to the right of g of x is now positive infinity. Okay, I'll leave these two for you to work through on your own. I definitely encourage you to take a look at it because it will absolutely be helpful. And now for a quick, very, very quick look at horizontal asymptotes, right? Horizontal asymptotes happen as x goes to plus or minus infinity, okay? This is something that we, very briefly talked about when we were doing limits at infinity, right? Looking at something like this, right? What's the limit as x goes to infinity of that first function, x plus 1 over x minus 1? And there's a number of ways to, think about this and work this out. We sort of looked at what happens when you multiply by 1 over x over 1 over x, and you end up seeing that the limit of this is 1, right? So that means as our function gets larger and larger, either way, we're approaching the number 1, right? And the same logic here actually works for both plus infinity and minus infinity. Okay, so this horizontal asymptote stretches both ways, right? Similarly, we could take a look at the function that we call g of x over 4 minus x squared. And here, once again, there's a number of different ways to think about it, to sort of go about it. But we looked at doing this, right? Multiplying by 1 over whatever your highest power is, right? And if you work through that like we did back in the beginning of the quarter, you'll get that this goes to -1, okay? And these allow us to deal with rational functions a bit easier, okay? But thankfully, when we're graphing, something like a polynomial, right? This is a lot simpler, right? Polynomials don't have horizontal asymptotes. They don't have vertical asymptotes, right? they're continuous everywhere, and their limits at infinity, right? Either go to plus infinity or minus infinity, sort of depending on the parent graph.